Welcome to Fun Project Monday. On Sunday afternoon at 3 o'clock. Almost 3 o'clock. A little bit after 3 o'clock. But doesn't matter. It's prime time everywhere you are watching or on replay. I have some coffee to make it better. And this is a stream where we build something electronic, nice. Some nice electronic product. Just for the shits and the giggles without product managers, deadlines or whatever. We're not even doing it on Monday like the name would imply. But I want to get this product ready, so get some music. And so I want to build, I want to simply continue and have this ready. Because it's, I like to have my products finished. So let's start, let's get back into the design. So we were building, currently at the PCB design stage of our design. Last time we finished this area here. That's the front plate with all these switches and LEDs. Delicious. I even got an idea how to use the now more the now extra LEDs that we have. We can use it to indicate Wi-Fi mode if you're using Bluetooth to control it. Something like that. Have an LED to indicate that it's dark, so it's not dark anymore. So that wouldn't make sense, but we can add an identifier for Wi-Fi and Bluetooth. That would be pretty good. So let's continue on power stage layout. Of course, what I last time didn't realize, that's really small. That can have. Last time I was somehow thinking, shit, here's a radius. I don't want that radius, but actually that's not bad. It's small, so there can be some radius, some radii, I think. And we are working on the actual layout of the switching converter. And for that, I found a reference design from Texas Instruments, which has a very interesting, I can see my face, a side note. So, that is the, no, not that. Right, that PDF open. Oh, and last time I checked that graph, I didn't manage to read it off logarithmic a logarithmic scale correctly. Of course, here that's 3 ampere, and we get 90% efficiency, and that's great. That's really great. So we need to open it. And here we have everything. And we have a reference layout, which we could copy, or which we can get inspired by. But I don't know if that's a good idea to use it, for following reason. It's based very generously, like, I would have imagined that they have taken more account into getting the parts more together. So maybe it's good enough, maybe not. One thing which I've noticed is, of course, everything you want to sell in the EU needs to have an EU declaration of conformity. And normally there is a norm, there is an, how do you call it in English? So there are certain directives and ISO norms and EU norms which describe the kind of norms which they consider during designing, and it only has the HOHS R. No, RHOS directive in, so that you don't have too much lead and too much cadmium and too much heavy metals inside your product. But they didn't have any norm regarding EMI emissions, interestingly. So yeah, I don't know if it's on, if they have considered EMI in this design. I only gone through it very, very quickly. Let's check if there are any EMI considerations. Let's take a look. Given a table in order to reduce EMI. Yeah. Okay. So okay, the only mention of EMI is that they use some jitter to reduce it. Okay. Mm-hmm. Mm-hmm. Yeah, nothing more about this topic. That doesn't matter. I will open it side by side. One thing which I found interestingly, that they put the switch input, that's the switching pin, like this is high current, and that goes through to the coil, that they put that under the input capacitors. Found that very interestingly. Well, yeah, let's get back to our design. So, let's continue further with getting this switching path ready. Because one thing that we are not allowed to do is route the switching path. That's that, and from up here to this pin. This pin is also somehow directly connected to some of the parts. Oh no, that's the enable. So enable, that's a switch. That's ground. V in. Feedback. Enable. So that needs to be coupled back. That's the switch. Right. And up here, that's effectively the out. Yeah. Okay. But we will take one thing from the design, like we will route the switch under the coupling capacitor, under the decoupling capacitor for our power supply. And because the top pin is ground, we can have a ground plane going through the inductor. That should not be a problem. And the power supply is more or less on the more or less isolated from that high switching stuff over here. So let's start doing this. We'd need a wire and okay, and then relatively thick one. In this case, we will use what we can use, as much as we can use, because you want to keep the losses in that area of the circuit low, because we already got some. That should be a little bit. Oh, that could be just enough. So let's connect this. And now we need to route that switch output under the PCB or around the device to the like for some reason in the other datasheet available there was an hint of using of routing the signal around, or did they simply had another design here? Let me check. Switch. Oh yes. This boost capacitor line that needs to be routed around. That's important. So we don't need that heavy populated pack, but we could still use it to increase the so the question is, we could save all the vias. Actually, we don't need that. We don't need all these vias, fortunately. So we can remove those. I don't know how much current will flow through the boost capacitor. If we okay, let's change that. I don't know how much current will flow through the boost capacitor. Certainly the voltage changes will somehow result in a current there. So let's keep 3. If we keep 3, that should be pretty safe. So there could be some sort of loss in the startup. Let's take a look on the reference design, what they are still. We should. Currently, I'm really not sure. Actually, normally it's more or less good practice to keep the design on one plane, or as much as possible at one plane. So yeah, we'll keep it like this. We'll keep this connected and use 3 vias. And use 3 vias to transfer the loop to the boost capacitor. So we make it. Well, now we can space them out a little bit. And then connect them. I will do a ground. I'll do a small plane to do this. So it was this, yeah. Let's build a small plane for that. And keep everything as low impedance as possible. Okay, now we have a problem that the polygon thought it was wasn't part of a via, and because of clearance issues, of course, it won't. Will not flow into the. It will not flow into the vias. So let's see, properties. Connected, connectivity, add to net. How's this net code? That's net 15, net 5, okay. properties connect to net 5. Net 5, okay. So, and now we can connect it up here. That's not quite okay yet. We still need to make it a little bit... so that's okay. And here we still have enough space to pour a ground layer in. And because we need to... because the part needs to dissipate a lot of heat. Yeah, so we give it a little bit cooling over this path. That's not a problem. So we won't need that. And then we can connect all the let's change the basic. Where can I change my net classes again? Objects properties. I think this current doesn't need to be... No, that trace is not required to be that thick. After the specification on the datasheet or after the board layout scheme. So we won't do it. And then we can have high amounts of ground plane. Of course, now we are not able to add the C3 accordingly. Yeah, so we do it underground. So we get another pair of rings. So we'll delete this line here. Yeah, we do it underground. Check that they are connected to the mouse pointer. Merge net. Okay. Okay, that was wrong. We didn't want to move a net. That's correct. Okay, and let's disconnect all of these. So connect to net. Okay, let's merge them. Okay. So now we can use this polygon, we make it a little bit bigger. Get exactly this arrangement and put it on this side here too. And we will sponsor 2 more. So we get a little bit more of low impedance path. Although, let's keep it at them first. So pour that again. Update, yeah. Connect it down here.
Let the beat rock.
Connect that together like this. Like with this thick of trace, I could almost save myself the problem of connecting all of these. So connect to net. Let's check that. That is net properties. Net properties. It's net 5. So that shall be net 5. Okay.
Let the beat rock.
Okay, but why did Vane not get that on the first page? I don't know. Move. No, it was wrong. I think I need to do it in this way around. Okay, let's delete all of these. Delete net. I think that's faster if we do it from here. Yeah, now that's all one net. And this one we can do with and pour. That's faster. So we simply pour a very spacious amount of copper in here. Pour connectivity will connect it directly to the correct net. It was net 5. Okay. Of course, we can make that look a little bit better. Okay. And then we can pour that again. Good. And from up here, because that's one big pad, we will pour that on. So we will still have the pad exposed later, but the solder mask will have the right dimensions. Okay. So we'll do this too. So connectivity will directly connect it to net 5. Okay. So I want to know what the problem here is. Let's check that properties. Properties net 5, okay. I assume that they weren't that happy with being connected like this. So we simply add it directly with the port. Insert points like this and like this. Of course, we need to connect. We will need to really select the port to get the point. And now we can add it like this. Update it, and hello. We're now directly connected to the switching output. That's great. And now we can make ourselves enough space for the decoupling capacitors. We'll be placed like this and like this. Much space is that? I really don't want to move much space is that. If that's not enough space, we will that are 0. Yeah, no, that shit. We don't do this. We will move that a little bit to the side and make that a little bit smaller. Maybe move this a little bit. Okay, like that. I don't do this. I don't like to do this, but that should now be a little bit easier. Although they are connected later, so let's keep it more or less not too complicated to solder later. Because I want to build at least one of these, maybe more. And if we'll send it to manufacturing, we should make it too complicated for them to manufacture it, because it will make the yield will make the yield worse, and no, we don't want anything of this. Okay, let's add the output capacitors. Can be directly added on top of here. Like this. Yeah, that looks good. Let's give some space to the inductor. And after the power supply, after that, I will directly add the ground plane around this area. Because should you put a ground plane around an inductor? We'll keep it around, that's not a problem. because later we so will have lots of no, don't do it yet. We'll first add all the other components. Okay. C1 is the check. C1 goes down here. That's part of the feedback. Also, there are also should also be some resistors that are associated with it. And let's check the schematic. And with schematic we can check if which resistors are the most important for the LED channel 1. R3 to R6. R3 to R6 for first, so let's start with them. Let's start with R3 here. R3, 7. R40, yeah. Need this one. And R3, R4. R5, R6. R6 is the wrong size, so we'll change that very quickly. Because we don't want to solder that kind of device, that kind of small device. And R7. Oh wait, it's an 0804. Oh, but R6 got to be in 04 too. Yeah, no, we don't solder that. We won't do this. We will not do this. Okay. R7. So let's first of all start. The first resistor is R3, R4. So the feedback loop starts here. So we'll put them directly after the place them directly after the output capacitors. So our feedback is definitely filtered. From that we can do well, we'll put them down here. That's not a problem. R3, R4 gets so it gets down here. Okay. 3, R4 and C1. Let's put them directly beside each other. Okay. R7 goes here and is connected to R. Oh, that goes to ground, okay. Directly here, we can change the different markings later, and we will rotate this 2 times. Okay, and put that accordingly here too. That goes down to where does that go? R7. What does R7 do? R7 is... Oh, R7 isn't part of the voltage divider anymore. Okay. So we're not that interested in this one yet. And R6 is is part of a voltage divider together with Q2 and RQ29. But we'll change that first. Replace part. That needs to be in. How much is, what kind of value is that? That's an 08. So that's need to be in 08, 05, W, 8F, 8F, 8. 8 to 1. That could be a correct one. Okay, that's now corrected, and after we have replaced it and updated the schematic, we should be good to go. No, not yet. By reference design schematic 2. Okay. Okay, why did R6 didn't change? Did we change now? Oh, we changed the wrong schematic. Okay, that's not very good. File open recent, because that's only the schematic and not the schematic 2. Yeah, we need to. Oh no, that means that could be very bad, because in worst case we have now destroyed the whole design above here. What? That still looks good. Okay. So nothing happened, great. Now we can use the second design to make it more, make it better, and change and replace this part down here. So we want to have this one, okay. And we will directly replace it here in the channel 2 and 3 2, because then we don't forget it. Place part, filter, apply filter. Okay. That's now an 0805 part, great. I'll do it here too. Place part, filter, apply filter, and replace it, please. Do. Okay. Save it. And now we will import it again. Okay, R6 is now an acceptable part, which we can add to the bottom side of the feedback loop. And replace and remove this kind of pouring. And together comes Q2. Q2, 2 and 7, yes. With a resistor, and that should be a resistor, let me check, 20, R29. With R29, perfect. Now I'll take those and use it here too. That's ground, so yeah. Great, so that's good now. R7 is later part for the 7 will be part of the low that circuit. So R7, Q7, Q6, R7. Yes. Q7. Q7 and Q6 is Q6 for R25. So I get these parts. And Q6. R51. Yeah, so let's get these two. Do we need something more? Currently I'm... That should be correct, yes. Yeah, it's... Did we place this MOSFET the right way around? That's an NPN one, and I don't... Did we place our MOSFETs the right way around? I hope so. No, we didn't. Oh, shit. No. Or did we? No, we didn't. We're all placed the wrong way around. Great. Good that we notice it now. And not later. Simply disconnect wires. And simply flip it. Vertical. No. Horizontal. Yeah, now we are correct. Shit. It's... Oh my god. Tuck them away here. Yeah, that's something we need to change now. We cannot keep that like that because that's not good. Although that would mean that the body diode is I'm somehow wait. That would mean that the body diode isn't connected correctly because the body diode is not allowed to be conductive, and yeah, that's correct like this. Okay, we didn't make this wrong, yeah. Sometimes you really get... Okay, everything's good. Everything's good for sure. Oh my god, that would be a real bummer. Okay. Let's continue. So R51 is the driving resistor here for this. We keep them connected nearby. Same thing here. R7 is the pull up. 7 should be the pull-up resistor for the output, yeah. So he gets placed up here. Let's keep them all in one line, that's nice. Rotate them correct. Down here. And R25 is... Oh yeah, R25 is the drain resistor that can be far away, that's not a problem. Like R51 is also allowed to be far away. So these two get connected together. Because he will be driving a lot of current. That's our power transistor, correct? Yes, that's that AO part. That's our power transistor. Yep. Okay, and then we have 3 not so powery. Oh, 3 more power transistors. Yes, Q5 to Q3. So let's get those, Q5 to Q3. Q5. Yeah. Q4. Q19, yeah. Q3. Q3 and Q4. But these are directly connected to our wires. These will be connected directly to our wires. G1. Do I have every one of them? Q3. Yeah, this one yet. So let's get this one too. Okay. So before we do anything more, we will place the markings in more acceptable manner. We'll bring those feedback parts up here. So we can later have a ground plane coming through here in, because we still need to have ground contact and everything connected to the ground here. So we can pull this through that gap, and then we will have our feedback coming down, and that's okay. But for that, and because we have some space, we can place those markings directly in an acceptable manner. Yeah. Like this, C3, C2, of course also. And these markings will go down here. Make a new layer down here, so like this. You want here space for this marking, and R6 is the R6 is to be placed relatively near here. Down here and down here. Yeah, R29 is not that critical. But I want to have the ground path as short as possible, for sure. Okay, and then we'll directly clean up these designators. this, and well, yeah, like do it like this, yes. That's great. We put it up here, because we put it up here we can make it a little bit smaller, as we don't have unlimited space. Should have quite enough space for everything, but still not unlimited. Q6. Okay, so let's make some space up here. Do we have everything? No, we still need to put in the power transistors for the RGB mode. Those can be placed red. Is that the red one? The red one RGB, so you start with Q4, 3 and then 5. Okay. So Q4, 3 and then 5. Check something. Let me check something first. Okay, let's continue here. So Q3, 4, 5. Because YouTube always asks, is it made for kids or not? And I think to be visible or really visible, it needs to be sure that it's not made for kids. For some reason, Twitch doesn't need that. So yeah, Q3. So I want to have Q5 up here. So my goal is to place all of these directly in the right position, so I can then simply copy the different coordinates with an offset to have everything layouted the same. I don't know if DipTrace has a function for that. That's something we should see if we can find that out. Okay, that are our 3 transistors. And they have some logic here. Let's put all of the R51 is the pull-up, right? R51 is the pull-up, yes. So a pull-up can be placed. Yeah, fuck the... Let's don't care about the RGB scheme. Let's simply place them like this, so I can directly connect the pull-up resistor. So yeah, now we are already way too wide to place all the different channels, so we still need to get a little bit more tight, a bit smaller, and that's good. Now let's continue. So does the switching has another resistor? R7, yes, and that's all in R25 is okay. I'll have all relevant parts in, and after that we can start putting some wires in. Yes. So want to add some net classes. Where can I add my net classes again? Net classes. So our default will be 2mm trace width, because of course JSC can produce 1mm or 0.1 millimeter, but we don't need to do this. Let's actually we could do 0.3 is that's actually pretty good for the manufacturing and manufacturing yields. If you make them a little bit bigger, it makes everything easier. So net classes, yeah, let's make them 0.3. That's way more than enough. We don't have such a high density layout where we would be really prone to having not enough space, so we can take our. We don't have problems. Simple as that. So let's put it like this. And from here we will go down. Yes, from here we will go a layer down, because here we'll go layer down, because we want to have as much space as possible for our ground plane, which is allowed to protrude around the bottom part. Actually, pretty important. Up here, that will be all made by pores. That's not a problem. That's a big pad. That's we will heat it up with. It will be fun soldering this, but yeah, that needs to be relatively thick. I will add another net class. Net classes. Oh, let's give me a PCB calculator. Was Galaxy PCB calculator was the best one. No. No, not that one. Was it Jupiter? There was some PCB calculator, Saturn PCB calculator toolkit. Okay, you need to download it. Yeah, let's do it. Let's get this one. So, give me Google. And PCB calculator. Let's get this one. So finish. So let's get Ohm's law. So I'm pretty sure that we will get. Does this have bandwidth, conductor length? Nope. Impedance is not important. Version, wavelength, via properties, thermal management using. Nope. Okay, that would be somehow Ohm's law. So for ohms we have. So we want to have a voltage drop of, let's say, 1% at 5 volts. So that's the worst case, and 3 amps. So 5 volts and 0.05. At floating point, okay. So we are allowed to have 0.016 ohms, okay. And that's, do I get a trace? Do I have a trace calculator? Attenuation, parallel options. Okay, here I can calculate. Why can't I do this here? Can I solve? How can I turn it on again? Okay, that's not the right one. No chart. Okay, I'll do a quick break. I'm back in a few minutes. Okay, let's continue. Okay, I have no idea why this doesn't work currently, so I don't care about it. We should. But let's keep it like this for... Let's keep it like this for... Yeah, let's care about that later. We have plenty of time and plenty of other things to do. So, then of course we do need our feedback loop. That's ground. Yeah, that should be ground. Why is ground not named ground as a net name? Netlist, net2. Net properties, net name, ground. Way better. We'll change that in the schematic later, because if you do an update, it will get confused. So we'll need to think about that. We'll replace this line here. And connect it with relatively normal trace and not too often miniature trace. Let's do this. And let's do that. So this is also not a high current path here. We can do this. Okay, that's the output. What's that? That is channel 1 out. Okay, let's get later. Okay, but that's not high power. That goes all through the through the 100k resistor, through the to the output, so that's not a problem. One thing could change. We will arrange them like this, because after we have arranged them like this, the possibility of I don't think like this will all need to go to ground. Yes. So I have a massive ground plane here. Okay, like this. So this part of the ground plane is extremely important, so we make it a bit more accessible. Okay, and now when we are from the sides, we note that R19 is so small. Oh no. So now let's check all the surrounding parts. So R25, we need 26, 27, 28. Okay. So let's check for parts and get those. 25, 26, 28. R25, 26, jawohl. 27, 28. These are most probably two. So one of them. Let's get these first. So, and 28. 28, please. Okay. And let's get this one too. So these are all the resistors for the MOSFET gates. And to connect them, can simply have them laying around here. Because if they are placed around they can be routed relatively easily, and if they're accessible in one row, that's easy to do. That's easy to manage, and so we'll do this. So we'll do that. R27. Yeah, well, yep, looks good. R26 is here. Later in software, you of course need to think a lot about interlocking the different outputs or the different transistors, because if too many are running, or if the wrong are running at the same time, That's not good. So 25, 26, 27, 29. Do you need 32? 30, okay. Everything from 25. So 25 is here, 26, yep, 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 yep. No, not yet. So we get this one too. And that. That will connect. Where does this connect? Which queue is it? Which is... That's Q1. So let's get Q1. Q1. Let's get Q1. And Q1 is the enable. It's the enable. Yeah. So not that critical either for sure. Can be connected directly, yeah, no problems. Let's keep here some space. Okay. Let's get these down here, because then we can have those very simply connected on there, and that's good. Okay. Let's make them a little bit less spacious, so have roughly the same space between each other. That's great. So now that looks everything. Is that all for the first stage? Could be. That one is missing. What's the control for Q6? Oh, Q6. Okay, that's the control. Okay, we don't need it. Okay, then we can certainly start adding those. Those control lines. Can stay as long as possible at the bottom. Like this. Here we will also keep that yeah, we do it a little bit differently. Go down here, move it down there and down like so. Because now we have lots of space for routing the rest of the control lines. Because these don't need to be that straightforward, they have lots of space for arriving at the we have lots of space for getting there. So we do a nice fanning down there and yeah. Move them part by part to their destination. Keeping the ground plane as free as possible. Oh, here, get. Well, because we need to have space to get the ground plane and the high current vias through there. Not yet. Let's go up here. It's like this. Okay. And let's move them a little bit more closer here. And we can place those here and like this. So move that one. No, not everything. I only want to have a specific segment. Unroot segment, yeah. And from here we will emerge on the top. And make our way to here. Great. Like this. And this should be angled. Great. So now this is connected to. And we'll remove this here. It doesn't look good. And that is allowed to have more space. Like this, okay. That too. Oh, that doesn't look that nice either. Let's build it like this. So that's better. Let's move this to the side. We don't need it here. Like that. Now we can almost start adding a ground plane. Ugh. Which will connect everything here. So let's put this together to the side. Let's put this a little bit more to the side also. Okay. Now we have less problems inside here. And we can, where is that ground? Okay, we can make this a bit more sneaky, because we make this sneaky. We have the middle part completely empty for the ground. We will do the same here. Because we have so much space. I simply say we want to keep the top part as clean as possible. And from here we will add the ground plane. Like this. If we emerge those contacts, we should get an clearance and some heat decoupling. So we'll simply do it. And pull it up to here. Run it around here. Here, here, here. And fan it out at for first. Because if you have fan it out, or if it placed outside everything is way easier. Okay. Good. So first we'll start with adding this to the ground plane. To net ground. And thermals, we will do some spokes. Okay, and let's see. Yep. I'm happy with that. Can certainly merge all of these two, and then they get connected too. Let's connect everything from here on. And see what happens. And give me an update. Okay, that island here is of course not that nice. Not that nice. We can increase it by half an... Yeah. Island's okay. Yeah, I'm thinking about adding an... like I'm really happy with having those connections here, but I would certainly enjoy it more if these were connected directly. Also, maybe we'll do here a second one, or a second. Oh yeah, we'll need to connect it down to the IC too, so we'll insert a few points. And connect it on there too. Ah, no, don't move everything. And here we will do some via stitching later to get the heat out. Get the heat out of the small device. Of course, you could also try to calculate the heat dissipation and the amount of heat transported out of the device. Yeah. Okay. Yeah, I will change that down here. So that will certainly be changed. But that and that maybe too, but first of all it's okay. So these will get connected to the side. From here on, there will be these connectors here, or these wire headers, which will be arranged so they are easy to connect to the actual device, like this. Okay, let's do this. Okay, that looks good. Now these will be, after I removed all of these signs, they are too much. They are too much currently. Why is LEG1 up here and the R, B, G and R? Okay, G1 is actually 2. Okay, good. So then connect those. It's another class, millimeter trace for power. It should be okay. So we will tools, we will verification, high speed, root, placement. Net classes, we will add another class, add for power. Name it power 1. And this class will be 1 millimeter. One millimeter width. Okay. So we can get some power out. I wouldn't trust that design check. We'll need to check that. Just remove that again and do this. And repeat that. This. Down there. And a second wire. Let's put it down here. Of course, also and this can now be placed somehow like here. This trace needs to be bigger because that's the actual because of this trace we will have a current flow of 3 amps, and all of the others will have a current flow of 1 amp, so this will need to be a little bit wider. So wide that I would say we could solve that problem with an via with a plane, or remove this one quite to the front. But first of all, check a little bit about space. So now we almost know how big the module will be. Let's clean up first. Let's clean up here first and see how well our layout is and if it will still fit on the base plate. And if we still can be that relaxed about everything, or we need to be really thinking about space. I would assume that it will be. Yeah, we should almost build it a little bit wider. Or move all of these resistors to the bottom, but we would be able to locate 3 of them here for problems. And that's certainly possible. Even having some space to the front, so the assembly of the wires is easier. Which is something you want. Quite certainly want, yes. Okay, we are now at 1.5 hours. Yeah, that's good. It's good that we have designed this part as objects. Can I make the red lines invisible? There was an option to do that, but yeah. Well, that's good for first. After we have arranged the first one, we'll still need to think how to solve the problem with the wire up here. Let's do let's do it very simple. Let's place it like this. And simply do a trace. And simply do an yeah, if you do we will simply do a plane, because that's a lot of current and I don't want to have any noticeable voltage drop about there. I'll simply fill it and then it's good. Oh no, we don't need a plane, but we will do it in the next stream. Goodbye, internets.